Students, our today's topic is electric field due to uniform spherical shell of charge. In the previous topic, we discussed the electric field due to uniform volume charge, spherical volume charge distribution. There is a difference between sphere and spherical shell. The sphere is dense from inside. You can say that it is filled from inside, just like a hard cricket ball. On the other hand, the spherical shell, in case of spherical shell, the shell is hollow from inside. Means there is nothing inside a shell. Shell is hollow from inside. We will consider there are two shell theorems for it. We will consider first theorem by considering a spherical shell of radius r. The positive charge is distributed on its surface. You can see that it is hollow from inside. And the first shell theorem says that
One.
the first shell theorem says that for external points, means if you want to calculate the electric field on its on the external of this spherical shell, it will behave like that the whole charge is concentrated on its center. Let us calculate this. We consider a Gaussian surface of radius small r. Here the r is greater than this r. We consider a point P here. Now we will calculate the electric field here by using a Gauss's law. The formula of flux will be E dot dA. If we consider a point area element dA here, and you can see that because of the positive charge, the electric field lines will be outward, and the angle between electric field and the area vector n will be 0. So E being uniform also can be kept out of the integral. This is the area of this, and also we know that flux is equal to charge enclosed over epsilon naught. So by comparing equation number 1 and equation number 2, we will get E is equal to Q over epsilon naught 4 pi r square, or E is equal to 4 pi epsilon naught r square or unit vector in case of vector form. And this is k, 1 over 4 pi epsilon naught is k, so kq over r square. This is the case of a point charge. So you can see that for a external point, a spherical shell will behave like that. The whole charge is concentrated on its center, and the value of charge is, you can see that by applying by using definition of surface charge density BQ. If we consider an area element dA, dQ is equal to sigma dA and Q is equal to sigma 4 pi r square. This is the charge enclosed by the Gaussian surface. Now we will see the second shell theorem. According to second shell theorem, if a charge particle is kept inside a positively charged spherical shell, it will experience no force. No electrostatic force will be experienced by the charged particle kept inside the spherical charge distribution. Also, again, we will consider a Gaussian surface of radius r. Now r is less than r because we are calculating the electric field inside the spherical charge, uniform spherical charge shell. This is point P. Again we will use this formula, sigma E dA cos 0. Again the angle between them will be 0 degree. E dA phi, its value will be 4 pi r square. Question number 3. Question number 4. Q over epsilon naught. Now you can see that there is no charge enclosed by the Gaussian surface. That means the value of Q will be 0. So flux will be 0. Comparing these equations, we will get E is equal to 0 degree. E is equal to 0. Sorry. The value of E inside the uniform spherical charge shell is 0. And we know that the formula of electric force is QE. So no force will be experienced by the charged particle kept inside the uniform spherical charge shell. This is our today's topic.